Welcome back to the course on C programming and assembly language. So in the last couple of lectures we discussed two kinds of 8086 instructions. One is the data transfer and the key summary for the data transfer is we did move destination comma source and the source was unchanged. Unchanged in the process, data would move from the source to the destination and none of the flag registers would be affected in the process. We then moved on to discuss a few ALU instructions. Like the add, subtract and XOR and all those instructions were bitwise operations. So the logical operations were bitwise ops. So we will continue with the ALU instructions in this discussion, and we will introduce two very simple but very important instructions here. So in this class we have the increment and decrement instruction. So what we do here is we could do the following: inc AL, which means increment the value of AL, right. So what does this do? It just replaces AL by AL plus 1. Alternately, you could also do it on AX or you could do it on EAX. So this is a way of implicitly adding 1 to the register without calling the add instruction. Similarly, you could do a decrement AL or AX or EAX. So what does this do? It will simply replace AL by AL minus 1. So this is an ALU operation, so implicitly the flags will be affected. So if AL for example happen to be 0x0001, right, oh this is 8 bit, so it would just be 0x01 and you decremented AL, then after this instruction AL would now become 0x00 and hence the 0 flag will be set. So moving on with a few more ALU operations, the next important operation is the compare operation. So the mnemonic for this is CMP. I could do AX comma BX. So what does this do? It simply performs the operation AX minus BX but does not put the result into any register, which means that both AX and BX are unchanged in the process. So if none of these registers are actually affected, then what actually gets affected in the microprocessor? It is only the flag registers. So what is the use of this instruction? It is used when you want to affect, compare two numbers and then make a branching or a looping decision in the assembly language. So it affects the flags, and based on the flags I could do a branch or a loop, which I will cover later in my in another discussion. So similarly you could do this with compare BX comma CX or BL comma CL, right. This is 16 bit, this is 8 bit, or you could do ECX comma EBX and this is 32 bit. And with any ALU operation like I mentioned earlier, you can use any kind of addressing, which means that you could do CMP BX comma ECX minus 4. So this is a register indirect with offset addressing that we are doing here, and we are comparing the 16 bits of BX with 16 bits pointed to by ECX minus 4, right. There are a few more interesting things that you can do in the 8086 architecture, which happens to be a string operation. Right, or a string compare. So let us assume that we have two arrays, or you have an array in a memory, right, and you want to search for a particular pattern. So let us assume that in the memory, in maybe 100 consecutive locations, I have a particular string or an array of bytes that have been stored. So this is my array of, and let us assume that this is maybe 256 locations. And what I want to do is to search for a particular byte pattern in this 256 locations. So let us assume that I want to see if some location in this actually has the contents 0x21. This is a very arbitrary number that I am just choosing here just to illustrate this particular operation. So let us assume that we want to search for 0x21 in 256 bytes stored in somewhere in memory. So let us assume that this address location starts at some address called data underscore address. So starting from data underscore address, I need to scan through 256 locations in order to see if any one of them has the pattern 0x21. So in order to do this, there is something called a scan string, SCAS, and since we are looking for a byte of information, I am going to call it SCAS B. On the other hand, remember that I can also search for a word or a D word. So as with all our earlier discussions, this is 8 bits, this is 16 bits, and this is 32 bits. So what does SCASB do? It compares EAX, right, or if it is if I am trying to do a SCASD, or it would compare AX, or it would compare AL with the contents of the destination index register that is pointed to by it. So whatever value the destination index has, it is going to compare one of these registers with either a byte, a word, or a D word pointed to by the destination index. And after you finish this operation, the destination index register is automatically incremented or decremented by 1, 2 or 4. Now it is decremented by 1 or incremented by 1 if we are talking about a byte, it is incremented or decremented by 2 if we are talking about a word, it is incremented or decremented by 4 if we are talking about a D word. So now let us see how we can use this instruction to perform the task that is given to us. Namely, we want to search for an array search in an array which starts at data underscore address and find if some location has a particular string called 0x21. So obviously because EAL or AL has to be the register that is going to be compared with, right. So we load this particular pattern with into the AL register. So what are we doing here? We are loading the pattern into AL. Now we need to search for the pattern in about 256 locations. So therefore we need to load this count into some particular register. So it turns out that there is a designated register that has to be used for this purpose, and that is nothing but the ECX. C stands for the counter. So by default any counter has to be loaded into the ECX register. So we are going to move ECX with 0x 0 or I will just move CX with 0x 0100. What am I doing here? Loading the count value, which is nothing but 256 by the way in decimal. Now also I have to initialize my destination index to point to that particular starting address. So move di comma so let us go ahead and add this particular instruction that we just discussed, which happens to be the SCASB. So what is this instruction going to do? It is going to compare AL with contents of DI, and then it is going to either increment or decrement DI. So how do you determine if the data, the address is going to be incremented or decremented? That is determined by the direction flag which can be set or reset. So therefore before we start the program we are going to do this operation called CLD, which is nothing but clear direction flag, so that the string operations work in auto increment mode. So after you compare AL with the contents pointed to by DI, DI will be incremented by 1. And why is it 1? Because we are doing a SCASB, B for byte, and therefore we are incrementing the address by 1. Now this unfortunately does it only for one particular location, right. So for example, if my memory had let me just illustrate with an example here. These are my n locations. Let us say this data in my data address was pointing here, and the data that is being stored in there is 0x okay, it's a byte 45, 0x46, 0x47 and 0x21. Remember that we are looking for this particular pattern 0x21, and that is what has been loaded into the AL register. So when I execute this SCASB once, then it is only going to compare this particular value with my AL register, which is 0x21, and of course the two numbers are not equal, right, but unfortunately we have still not been able to achieve the comparison with the entire array. So how is that achieved? That is achieved with something known as a prefix that we add to this particular instruction, REPNE. So what does REPNE do? REPNE is repeat until not equal or Cx equal to 0. So this is known as a prefix to a string instruction. So what do we call this? This is a REPNE is a prefix. So what we are doing here is, as long as none of the locations have 0x21, you continue this SCASB operation again and again. And what does the SCASB do? It just compares, then increments the destination pointer. So after the first operation, my DI, right, my DI was pointing here. After the first comparison, DI would then point here. Second comparison, it would point here. The third comparison, it would point here. So when it comes to the third particular value, it finds that 0x21 has actually matched with my AL register, and hence the comparison will stop. So what does this mean? When this comparison stops, ECX will simply be ECX minus 1, 2, 3. It will be ECX minus 3, right. So it will simply be 253. So the idea here is to use a counter, right, and if you do not use the counter, what happens is it can go into an infinite loop. So therefore you have to tell it how many bytes to go and check with. So that is the limit of the number of locations in the array or the string that we are going to search, and that is loaded into the ECX register. So you compare, you increment the destination index because the direction flag has been reset, and you keep doing this operation until you have encountered the particular pattern or the ECX register goes down to 0. So here I showed an example where this 0x21 occurred. Now what if this 0x21 did not occur? So instead of 0x21, if it was 0x22 and all the 256 locations did not have any of this the pattern 0x21, in that case the comparison will fail always and ECX will eventually come down to 0. So this is case 1. Case 2, ECX will simply be 0 because no location equal to 0x21. So remember that this is not a software loop, but it is a hardware loop, which implies that the instruction is just issued once and the operation finishes in one shot and only then returns to execute the next particular instruction, and therefore it is extremely fast.